We talked before about the value of information. And information is valuable only when it can actually change what you do. If even information itself is not created equal, then how can all knowledge be considered equal? You might read 50 books a year, fill notebooks with detailed notes, listen to podcasts every day, and save every obscure fact you come across. You may pride yourself on knowing a lot. At dinner, you can jump from geopolitics to quantum mechanics. That kind of knowledge may give you intellectual pleasure, but it may not be very useful. When something actually happens, you still don't know how to make a decision. When you read the news, you can't see the underlying structure. Someone asks you, what's going on with the Chinese economy? You can list the opinions of 3 economists. Their views seem to contradict each other, and you still don't know which one to believe. At that point, you might as well ask AI. Or even a search engine. A lot of people have been misled by exam-oriented education. They think learning means memorizing knowledge points. They don't understand the real value of learning, or how learning actually works. Today, I want to introduce 4 concepts that your high school teachers probably never taught you. Representation, schema, mental model, and explanatory framework. Together, they form 4 levels of genuine learning. Let's start with why listening to a historical story is not necessarily learning, even if the story is completely true. The same goes for an impression you get from visiting a tourist attraction, or 20 years of experience accumulated by a master craftsman. What you receive is information, not necessarily knowledge. Information helps you overcome uncertainty. Suppose you don't know whether there is oil under a particular piece of land. Someone tells you that there is. That's valuable information. But it isn't really knowledge, because you haven't learned a skill. If you move to another location, you still don't know how to determine whether there's oil underneath. Information is giving you a fish. Knowledge is teaching you how to fish. Knowledge is a general method of operation. Once you have it, you can go somewhere else and still catch fish. You might think knowledge must be much more complicated than information. Actually, it's the opposite. Knowledge is not about complexity. It's about simplicity. What did the fisherman eat this morning? What brand of fishing rod did he use? How much did his bait cost? Was he arguing with his wife? Those details may be important to a complete story, but they are irrelevant to learning how to fish. To learn, we have to throw away the irrelevant details and extract the general structure. Around the year 2000, Naftali Tishby, a professor of computer science and neuroscience at the Hebrew University of Jerusalem, developed what became known as information bottleneck theory. The basic idea is that whether it's the human brain or a deep neural network, learning is fundamentally not about memorization. It's about compression. Learning is compression. We want patterns, not details. The more concise the patterns you take away from a book are, and the more phenomena they can explain, the better your compression is. And the more powerful your knowledge becomes. A book that explains underlying principles is much more valuable than a book that simply tells stories. Someone may learn a simplistic philosophy of office politics from historical novels, only to discover that reality doesn't work that way. A scholar, however, may extract patterns from thousands of historical events, test them, refine them, and build a theory. That's real intellectual leverage. Stories are useful, but often they are merely the raw material from which we extract patterns. And these patterns aren't one-dimensional. They have levels. Let's move from the bottom to the top. The first level is representation. A representation is a substitute for something in the real world, inside your mind. Take the word apple. A real apple is a collection of atoms. But the apple in your mind is something red, round, and sweet. Modern cognitive psychology suggests that the brain doesn't directly process reality itself. When we think about the world, we operate on representations of the world. You don't directly think about economic activity. You think through economic concepts and indicators. You don't directly understand history itself. You understand a particular historical narrative. You don't operate on territory. You operate on maps. Representation is the smallest unit of a cognitive map. It usually corresponds to concepts, objects, terms, relationships, and boundaries. So when you enter a new field, your goal isn't to memorize every sentence in a book. Your first task is to extract the key representations. What are the core concepts? What are the most important variables? How are they related? If you can identify these representations and draw a map showing their relationships, you have begun to build a basic cognitive model. You have turned on the place names on your mental map. The second level is schema. We've talked about schemas before. If representations are individual cells in your mind, schemas are the tissues or muscles formed by groups of cells. The concept of schema was introduced by British psychologist Frederick Bartlett in 1932 and later developed further by Jean Piaget. Think of Lego. A representation is one individual Lego piece. A schema is a recognizable structure built from many pieces. You look at it and immediately know. That's the chassis of a race car. And because you know the schema, you can predict what comes next. Schemas are templates for pattern recognition. Someone who understands academic writing already knows that a research paper probably contains a problem, a method, results, and discussion. Someone who understands startups already expects to see a value proposition, a funding story, and organizational growth. A beginner looking at a chessboard sees a collection of individual pieces. A professional chess player sees patterns and positions. An outsider hears a boring speech. Someone familiar with the field immediately recognizes what kind of game is being played. Schemas allow you to recognize situations quickly because your brain can fill in the missing pieces. Bartlett demonstrated this in a famous experiment. He told British participants a Native American folk story containing many cultural details that didn't fit their expectations. When they later recalled the story, they unconsciously changed strange details or reconstructed them according to British cultural logic. This kind of filling in the blanks isn't necessarily bad. It's exactly how we generalize. Once you understand the schema of a platform economy, for example, companies like Taobao, Meituan, and Didi start to look like variations of the same underlying structure. Schemas dramatically reduce cognitive load. That's why people with more background knowledge learn faster. And why people who have read many books often read faster. If you have no schemas, every story feels completely new. If you have many schemas, you start seeing the underlying patterns. The third level is mental models. You can think of this as an organ. It doesn't just have structure. It actually operates. A mental model is essentially a schema that can run. The term was first proposed by Scottish psychologist Kenneth Craik in 1943. A mental model is a miniature model constructed inside the brain to simulate reality. The key difference is that it has variables, causes, feedback loops, and boundary conditions. It allows you to run simulations. If I do A, then B will happen. A normal schema tells you, what is this? A mental model goes further and tells you, how does it work? A complete theory describing how something operates can function as a mental model. Newton's theory of gravity is one example. The thinking tools we discuss in this series are also mental models. The difference is that we emphasize their practical use. When you truly understand a mental model, you don't merely know a concept. You can use it in different situations. Richard Feynman was famous among his classmates for his extraordinary ability in calculus. There were integral problems that even graduate students struggled with, while Feynman could solve them quickly. One reason was that he had studied an old advanced calculus textbook and discovered a subtle technique that wasn't emphasized in standard courses: differentiating under the integral sign. The trick itself wasn't the real advantage. The real advantage was that Feynman understood the underlying mechanism well enough to apply it flexibly to different problems. That's a mental model. Mental models are extremely popular in Silicon Valley and the business world. Elon Musk's famous idea of first principles thinking is a mental model. Charlie Munger famously collected dozens of mental models from mathematics, physics, biology, psychology, and economics. The real purpose of studying, reading, and researching isn't to collect more knowledge points. It's to extract the mental models underneath the material. How does this system work? What are the key variables? What goes in? What comes out? What affects what? What is the causal chain? Where are the feedback loops? Where are the delays and side effects? And where does the model stop working? Once you can answer these questions, you've actually learned something. The fourth and highest level is what I call an explanatory framework. This isn't a standard academic term. I'm using it here to describe a broader idea. An explanatory framework is a systematic way of understanding an entire field. It's the big map. It contains multiple mental models and schemas. It provides representations for the major questions in a domain and explains how a whole class of phenomena should be understood. For example, a major historical work about imperial China may not simply tell you what happened during the Qin and Han dynasties. It may connect economics, politics, administration, society, and culture. After reading it, you may understand why Imperial China developed certain fiscal structures, political institutions, and social relationships. You may also understand the actual roles played by legalism, Confucianism, and Taoism throughout Chinese history. Of course, no single book can explain an entire civilization. Different scholars develop different explanatory frameworks. Every serious academic field contains competing frameworks developed by generations of researchers. Compared with reading thousands of pages of raw historical records again and again, understanding a powerful explanatory framework can give you enormous leverage. This is when you begin to think like a scholar. You stop chasing stories. You start asking about mechanisms. You stop merely taking sides. You start comparing explanatory power. So what are we actually learning? We are learning to compress the world into an internal map that allows us to predict, explain, intervene, and correct ourselves. The basic building blocks of the map are representations. The reusable patterns are schemas. The mechanisms that can actually run are mental models. And the systematic understanding of the whole field is an explanatory framework. When people say they want to read a thick book and make it thin, this is what they should mean. Throw away the irrelevant information. Extract the representations, schemas, mental models, and explanatory frameworks. And then, when you make the book thick again, you're not simply going back to memorize more details. You're using your internal map to generate new understanding in new situations. So from now on, when you read a book, attend a lecture, study a paper, or analyze an article, don't just ask, "What is this about?" Ask, "What structure can I take away from this?" Representations give you the vocabulary. Schemas let you recognize patterns. Mental models let you actually use what you've learned. And explanatory frameworks allow you to judge what deserves to be believed, and what is merely a persuasive story. Finally, let's look at an extreme example of what learning might look like in the age of AI. In March 2026, someone on X reported that an MIT graduate student used NotebookLM, Google's AI research tool, to compress an entire semester's worth of learning into just 48 hours. He never attended the course. He studied for those 48 hours, then passed the final exam. So did he simply upload the textbook to AI and ask it to summarize everything? Not at all. In fact, he may have done more intellectual work than the average student. He uploaded 6 different versions of the textbook, 15 research papers, and all the lecture materials he could find. Then he asked AI 2 questions. First, what are the 5 core mental models that every expert in this field should understand? Second, what are the 3 biggest controversies in this field, and what are the strongest arguments on each side? From the perspective of today's framework, the first question is about mental models. The second is about discovering competing explanatory frameworks. Once he understood those 5 mental models and 3 major controversies, he asked AI to generate 10 questions to test him. For each question, he went back to the original sources and searched for the answer himself. He was forcing himself to read with questions in mind. When he got something wrong, he asked AI to explain why he was wrong and what he had missed. He was continuously refining the models inside his head. After 48 hours, he could apparently have a meaningful conversation with the professor. Personally, I don't recommend cramming. If you learn too quickly, even if you understand everything, you'll probably forget much of it. Learning more slowly and exploring more details can deepen understanding and improve flexible application. But this student wasn't simply cramming for an exam. He was actually learning. Because he understood what learning is supposed to produce. And if you've never done this kind of intellectual work yourself, even if you've spent 10 times as long studying something, you should still ask yourself one question. Did I actually capture the real thing? That's it for today's content. Thank you for watching, and I'll see you in the next video.